We will see now the normalization layers. So the goal of these layers is to keep the vectors in the different spaces as they progress through the network, to keep them in a somehow common region, because otherwise they may become too sparse, and the network has more difficulties to feed a function to this largely varying space, input space. So if you have, let's say, this is your normalization layer, this is the input to that layer. So the goal of that layer is to put the values back into a region so that points are again close to each other. We are trying to fight this curse of dimensionality, and for instance, here we are showing that if we do this normalization, again we are in a region of the activation function in which the gradient is large, and because the gradient is large, the network will be able to learn. But for instance, these points here, if we don't do the normalization, they fall in a region where the gradient is very small, and then there is no learning. There are multiple ways of doing this normalization. One of the most common is this batch normalization. So the batch normalization, if we represent the input data, here we have the different samples of the mini batch. So in the mini batch we have n samples. This would be the data corresponding, the slice corresponding to data one, to sample 1, sample 2, sample 3, and then we have multiple channels, and somehow here we are representing all the spatial dimensions. If we are talking about images, then the normalization is performed per channel. So for all elements in the same channel and all the samples in the mini batch, we are computing the mean of those samples, the standard deviation, and when we are standardizing, so simply subtracting the mean and multiplying by the standard deviation. And this batch normalization has two parameters to learn. One is gamma and beta. So these two parameters, they are also kept so that later, if we want, we can undo the normalization and recover the grayscale values into the original scale. So this operation, as a reminder, this operation is performed per channel. So every channel is normalized independently. Then we can have other kinds of normalization. So we can normalize by layers. So for instance, the same sample is normalized across all channels. Batch normalization we have already discussed. Then group normalization, we could divide the layers of a single sample into different regions and normalize by that region, or normalize by instance. This is called instant normalization. That is a single layer, a single channel, a single input. And here we are comparing these kind of operations to the operations we are doing with a 3D convolutional layers, or 2D convolutional layer. So we have the input channels here, the output channels, and then somehow here we are putting all the kernel. So the batch normalization somehow resembles a 2D convolution, considering all the mini batch samples as channels of the input. So it is somehow batch normalization is more similar to 2D or 3D convolution. So here we have a particular example in which we have different, these big changes are because of the learning rate. So there are changes in the learning rate. So here is the percentage of error validation set for a particular network. And what is seen here is that the different normalization techniques, they have an effect on the output. I think this sufficiently general to say that the batch normalization tends to give the best results, but this is always dependent on the architecture and the data set. But in general, it is true that batch normalization tends to give the best results. You see, the validation error is smaller depending on the kind of normalization. And sometimes you cannot make a network to converge if you don't do any kind of this, this batch normalization or any kind of normalization, because of this fact that the samples, they start to get very dispersed, and then they're falling out of the regions where the gradients of the activation functions are sufficiently different from zero. If they fall in very flat areas, there is no way that the network can learn. So with this we finish the part of normalization. See you in the next video.